seems like, sort of between 3 and 4 is definitely better than even 2. All right, so, and if I wanted to be, if I cared to be more precise, I could sort of do a bunch of more values in here to try and find out exactly where the minimum was. But in practice, probably anywhere in there is sort of equally good from the perspective of the leave one out cross-validation prediction error. So what is that? Oh, so I actually don't have a picture of what that interpolation looks like, but obviously it would be something with a bit more spatial structure than this. So it will be even more strongly red in here and strongly yellow in here, but not as blocky as this one. Now the leave one out cross-validation, or cross-validation in general, is not actually a spatial technique. Okay, we could do that with any model, right? We could do that. We could use that as a test of the quality of a regression model. So, and by just taking the average squared error, right? Nothing spatial about that as well. So I said that I mentioned that this is sort of one axis of goodness of a model. But because this is a spatial model, or a spatial process, it's important to ask, is there any spatial pattern in these prediction errors? Okay, so I fit I use the interpolation model with a P of 3.5, and then I asked, based on the cross-validation, I had those residuals from leaving out 0.1, what's the residual on 0.1? Leave out 0.2, what's the residual on 0.2? And so then I can look at, is there a spatial pattern in those residuals? And there is. So this map has again, the size of the bubble represents the value. The red bubbles have negative values, the green bubbles have positive values. And these are the residuals, right, the prediction errors for each point. So when I left this point out and used the interpolation scheme, the residual was -1. This point had a high positive residual. Okay, and so remember so the residual is the actual value minus the predicted value. So a negative residual means the actual value is less than the predicted value, so we're over-predicting. The positive residual means we're under-predicting. So although this is the model, or this is the interpolation scheme that gives the smallest mean squared prediction error, it's still, there's a lot of spatial pattern. Just from our eyes, we can see the spatial pattern that, along the shore, these are all positive residuals, meaning we under-predict, the interpolation scheme under-predicts those values. Okay? Just inland from there, we're over-predicting the values. And there's sort of some regions where we seem to be consistently over-predicting. Well, first of all, why is this occurring in terms of the patterns in the data? If we look, and 3.5, a P of 3.5 means we're giving pretty strong weight to the nearest neighbor. It's not, not like that P of 10, but it's still, the nearest neighbor has a lot of influence on the prediction. And if we look at, this is I think the P equals 1 surface, but just look at the size of the circles. We have these really high values right along the shore, and often just inland from them, relatively low values. And so if we take a point like this, its closest neighbor has a really low value. Okay, and so it's going to tend to be, you know, the prediction is going to look more like that value than like that value. So we're going to have under prediction. The flip side, when we look at this point, its closest neighbor has a really high value. Okay, so there's this very, because there's this very abrupt sort of shift here, and in many cases we have the closest sample is not along shore but across shore. We're seeing that effect. Yeah.
It seems like you have two interacting forms of spatial variation. One is the variation in the actual sampling pattern, and the other one is probably the variation in the actual pattern of how whatever you're sampling for is distributed. It wouldn't make sense to isolate some of that variation by having like a regular sampling pattern spatially, so that you can sort of see some of these things happen.
Okay. So yeah. So
I mean, is there an advantage to doing that, or no? Not really. Having a regular sampling pattern.
no. Well, that's an excellent question. And it's. I don't think there is a general answer. Sometimes it's advantageous, and sometimes it's not.
Well, I mean, from a statistical perspective, is it always
Even so, I mean, the disadvantage of a regular, one of the big disadvantages of a regular sampling pattern is that it sort of creates a minimum distance between your locations that you're never going to have any information about. Distance is small. And so, you know, if you already know something, well, so there's that. Another is that if the variation is heterogeneous, and you know ahead of time that there's going to be this large area where, yeah, the soils are all pretty much the same, and this area down here was a lot of variation, right? If you're using a uniform sampling scheme, you're, you know, in order to get good information here, you have to you're sort of wasting effort here. So
that requires some prior knowledge.
It does.
Of the heterogeneity.
yeah, and we can actually, I mean, if this is something that people are interested in, we can talk about sort of spatial sampling schemes at some point. Yeah, there are kind of there are adaptive approaches to sampling that can get around some of these issues. But you know, a priori, there's no one, you can't know which sampling scheme will be best without knowing something about the spatial pattern.
If you did know something about it a priori and you sample it accordingly, you could also maybe split the interpolation for different areas, right?
Mm-hmm.
Some other.
Yeah, you don't have to interpolate.
You
You don't have to interpolate over the whole domain. And for example, you know, given what we see from the data, one scheme might be to apply a linear interpolation that just runs along the coastline, right? So this, I mean, this is interesting because the analysis we've just done, this inverse distance plating, is often considered a non-spatial analysis. Okay? It's using distance, but it's using distance in a very crude way. Okay? And it's there's a number of. So what are some of the ways in which it's true? Well, one is it assumes that, you know, direction doesn't matter, right? All that matters is distance in any direction. And we can see, you know, just from the way this is laid out that you know, correlation, you know, that distance, the relevant distance is the rate at which the zinc levels change is much slower in this direction than it is in this direction. Right, so we wouldn't really expect distances in this direction to have the same information as this is the same distance in this direction, given that what we know now see about the data. So it says that direction doesn't matter. It also says that the location doesn't matter, right? The distance weighting is the same whether we're here close to the coast where zinc levels are changing really rapidly, or inland where zinc levels are changing slowly. Okay, that's the second way in which this is kind of, we're not really using spatial information. So we could imagine having, different distance weighting functions depending whether you're close to the coast or far from it. Distance weighting functions for, sort of parallel to the river versus transverse to the river. And then well, those are two of the big issues. The other is that by assuming this weighting function, we're not really asking whether this matches the correlation structure in the data. Right? What we would want is we would want the weighting function to, we want to highly weight, if at distances of 50 meters we see that plots that are 50 meters apart have a really high correlation. Distant plots that are 100 meters apart have a correlation of 0.5 and so forth. We could actually draw a map of correlation as a function of distance. And we would want our weighting function to actually be related to that graph, as opposed to an arbitrarily assumed function, which probably doesn't match what's actually in the data. And so we'll spend next week talking about that approach, how you calculate those correlation functions and then use them as in interpolation schemes. But that's for next week. The other thing I want to talk about here is this pattern of, the values seem to be really high close to the river and farther away, or lower farther away from the river. And so we might just say, well, let's just do a linear regression on distance to river. Okay, so for each point, we calculate, the distance to the closest point on the river, and then we can ask, how does zinc, can we do a correlation or regression analysis on that? And so if we do that, in particular, if it turns out that if we look at the log of zinc as a function of the square root of the distance from the river, there's this nice linear relationship. Okay. And that makes sense given what we see in the data. And this might be, we might want to be able to use this as a predictive model, right? We might want to say, well, if I'm 20 squared or 400 meters from the river, right, I predict that this is going to be the level of the zinc concentration. Now I've drawn a line through here, which is a linear regression line, ordinary least squares regression line. And so that's what that's what I pointed to when I made this prediction. And if we think about what are the assumptions of ordinary least squares in terms of, well, is the pattern linear? It looks pretty linear. Is it, are the residuals normally distributed? Well, hard to say just by eyeballing it, but it's probably not too bad for normally distributed. Is the variance independent of the prediction. Well, maybe the variance is a little small down here, but for the most of it, looks like the variance is about the same everywhere. So it seems pretty almost good. Are the residuals independent? Okay, which is actually, in some ways, the most important assumption of ordinary least squares regression, the one that, if violated, will mean not just that you have bad p-values, but that you actually, the slope of the line might be wrong. Might be systematically biased. And if all of the things I just said don't make sense, go back and review your notes on the assumptions of ordinary least squares regression. I mean, if all we had was this plot, right? There's no way to tell. You mean most of the other questions, do we have heteroscedasticity? Do we have normal residuals? You can make diagnostic plots to evaluate those. If all I had was a set of points that gave me, a data file with two columns, one that said distance and one that said zinc, there's no way to evaluate this question of are the residuals independent. But because we're in a spatial environment, we might hypothesize that points that are nearby, or the question is, are points that are nearby, do they tend to have similar residuals? Okay, and this could be nearby, well, just nearby in some sense. And the reason for asking that would be, or reason thinking that might be true is, well, there's probably processes other than distance that affect the zinc level. And those processes are not in this model, they're folded into the error term in this model. And the assumption of ordinary least squares is basically says that's fine as long as those processes are acting independently at each point. But if those processes themselves have spatial structure, then points that are close together are going to be similarly affected by this unobserved process. So, in this case, because we have spatial locations for each of these points, we can map the residuals. And here's what we see. So again, the size of the bubble is the size of the residual. Red ones are negative, green ones are positive. One thing that's reassuring is that there's no longer any consistent pattern along the edge of the river. So we have in fact successfully, accounted for that distance from river trend. But, here's a region where this model is consistently over-predicting the amount of zinc. Here's a region where it's consistently under-predicting the amount of zinc. Okay, and so, so these points are, they're close to the river, distance is small, they're all negative, so that's probably, but what it's saying is that these negative residuals in here are all close together in space, right? And, and this probably represents a cluster of residuals in here, okay? And so these are not independent observations in the sense that if we're thinking about, if we write down, let's see, how do I want to say this? Our model includes the distance from the river, okay? And then we have to, the error term is taking into account these other factors that might influence zinc. And the model is assuming that those other factors words, that sampling this point doesn't give you any information about the value at this point, other than how far it is from the river. Okay? But what we see is, in fact, knowing the value at this point does tell you something about the value at this point, above and beyond the distance to the river. Yeah.
So a simple way to include that effect will be just adding a fixed effect where they are along the river, not just from the river.
Well, if you think that that is, if you think that that's the model, right? That would be one. That could be one way to account for it. Does everybody understand what he just said? Do you know what a fixed effect is? What's the alternative to a fixed effect? Okay, you want to explain that a little more?
It's the, I don't know how to explain it. It's just assuming that you can group together some information that are more related inside that group than any other group. So it's somehow what I can see there, that if you define like 3 or 4 regions, you can probably increase the predictability or I don't know, or decrease the effect on your residual.
Yeah, I was gonna say, couldn't you like take a neighborhood range of residuals and then use that to recalculate the weights?
Very good. That's basically what we're going to end up doing. The correction for this. Rather than treating each of these residuals as being equal, uses geostatistical tools that look at, how basically what the covariance structure is in space,